Welcome to this explainer. Okay, let's jump right into this. We're looking at the escalating and frankly, fascinating arms race of modern fraud detection. Today, we're going to explore exactly how mapping hidden networks and then combining the raw mathematical power of graph neural networks with the reasoning capabilities of large language models is fundamentally changing how we catch bad actors. To set the stage, consider this staggering statistic. Confirmed fraud typically accounts for only 0.1 to 1% of all transactions or accounts. I mean, think about what that actually means in practice. You aren't just looking for a needle in a haystack, you are looking for a microscopic needle hidden inside an absolute mountain of hay. Because of that tiny percentage, fraud detection is structurally incredibly hard. Think about it. If you build a standard machine learning model that just defaults to predicting legitimate every single time, it's technically going to be over 99% accurate. But obviously, it's completely useless. On top of this extreme imbalance, we have relational behavior, meaning fraudsters share resources in hidden networks. And worse, they actively use adversarial adaptation, which is really just a fancy way of saying they camouflage themselves the second they know you're looking for them. So, here's our roadmap for this explainer. We're going to dismantle this complex problem piece by piece. We'll start with the core fraud problem, move into mapping the graph, and unpack how GNNs actually work. Then we'll look at how to battle that camouflage, bring in LLMs for a massive advantage, and finally, look at how you can actually build this architecture yourself. Starting with the core of the fraud detection problem, finding that camouflage needle. Doing this effectively requires a total shift in perspective. If you're looking at data in isolated rows, you're basically blinding yourself to the real threat. You see, fraud rings are lazy, but in very specific ways. They share devices, IP addresses, shipping locations, or phone numbers across dozens of seemingly separate accounts. Traditional row-by-row machine learning models like XGBoost simply cannot see those shared connections. They process one account at a time, entirely missing the wider relational behavior happening right behind the scenes. Which leads us to mapping the fraud graph, so we can finally see the whole network. This is exactly where we upgrade our perspective. We have to stop looking through a keyhole at individual data rows and get in a helicopter to view the entire network. We take all that chaotic relational behavior and structure it mathematically so our AI can actually process it. A fraud graph is what we call heterogeneous, meaning it has multiple different types of elements. You have your node types, like accounts, devices, or merchants. You connect them with edge types, like shares a device with or sent money to. Then you enrich the whole thing with features. Nodes get features like transaction velocity, and edges get features like timestamps. When you do this, you are literally drawing a map of the fraudster operations. So how do we analyze that map? Let's get into graph neural networks and the mechanics of message passing. Graph neural networks are essentially the powerful radar systems we use to navigate these networks. The crucial concept here is a three-step process called message passing. Think of it a lot like gathering intelligence. First, a node aggregates, or gathers, feature vectors from its immediate neighbors. Second, it transforms that gathered data by passing it through a learned weight matrix. Third, it updates, combining that brand new information with its own previous representation. Typically, you'll stack this process over 2 to 3 layers. That allows information to travel 2 to 3 hops outward through the entire network, generating a rich final embedding that classifies the node as fraud or legitimate. Now, there are a few foundational ways to build this radar. Graph convolutional networks, or GCNs, are a great, simple baseline, but they are transductive, which means they can't handle newly added nodes without totally retraining the model. Then you have GraphSage. This one is inductive. It samples neighbors and generalizes beautifully to completely unseen accounts. Though to be fair, the sampling means it might occasionally miss a rare, suspicious neighbor. Then there's GAT, which learns attention weights to automatically prioritize important neighbors. But even GAT has its weaknesses. It's pretty computationally expensive, and clever bad actors can actually trick its attention mechanism. Which naturally leads me to this big question. What happens when fraudsters actively camouflage themselves? How on earth do we catch sophisticated fraud rings that deliberately connect themselves to legitimate nodes, like buying a few normal items from trusted merchants, just to trick the GNN into thinking they're safe? That takes us to battling camouflage and imbalance using specialized fraud defenses. Because standard GNNs aren't quite enough against the pros, researchers have developed specialized architectures to fight back. Solutions like CareGNN actually use reinforcement learning to actively filter out camouflaged neighbors before they even have a chance to aggregate their data. Then there's GraphConsist, which measures relation-aware consistency, basically training the model to actively distrust edges that only look legitimate on the surface. And to fight that extreme 1% class imbalance we talked about earlier, PCGNN steps in to pick a perfectly class-balanced subgraph for every single training batch. Finally, temporal GNNs are absolutely crucial to ensure that a graph snapshot from last month doesn't accidentally leak into today's score by precisely modeling exactly when an edge formed.
Now let's talk about the LLM advantage and how we translate all this math into actual meaning.
This is where we introduce our secret weapon. Look, while GNNs are mathematically incredible at finding structural anomalies, they totally lack human-readable interpretability. A GNN gives you a bare metric, something like a risk score of 0.87. But let's be real, that is functionally useless to a human analyst who is staring at a queue of hundreds of urgent alerts. But when we iterate a large language model, it acts as a translator. It takes that raw math and turns it into an actionable detective case file. It reads the flagged subgraph and tells the human investigator exactly why the alarm is ringing, saying something like, flagged, account A shares a device with account B, which just sent $4,200 to account C. But LLMs do so much more than just translate at the very end. They elevate the entire pipeline. Imagine trying to manually read thousands of customer dispute logs. LLMs can easily encode that unstructured text, turning chat logs or complex dispute narratives directly into node features for the GNN to use. They perform graph-to-text reasoning over complex subgraphs. They can even solve the issue of label scarcity by generating synthetic fraud narratives for brand new emerging threats that just don't have enough real examples yet. And of course, as we mentioned, they generate those critical analyst-readable explanations. So if you're interested in building your own project, let's look at datasets, metrics, and domains. If you're looking to build this kind of architecture yourself, maybe for a scoped academic project, you absolutely need the right data. Here are some excellent candidate public datasets. For prototyping, datasets like IEEE CIS for card transactions or Yelp Chai and Amazon for review fraud are perfectly tractable. You can construct massive graphs via shared devices or IP addresses in IEEE CIS, or you can test those camouflage-aware models against collusive review rings in Yelp Chai. There's also the elliptic dataset for Bitcoin, which is a fantastic classic graph benchmark. But please remember this: measuring accuracy is a trap. I cannot stress this enough. When you have less than 1% fraud, saying your model is 99% accurate means absolutely nothing. Rigorous evaluation requires metrics like AUPRC, which focuses heavily on the rare positive cases and is the gold standard for imbalanced tasks. You'll also want to use Recall at K because that perfectly mirrors how human analysts actually triage the top flagged accounts in the real world. And crucially, if you are incorporating LLMs, you need a strict human evaluation rubric for the text output to guarantee there is zero hallucination in those explanations. And the beauty of this dual AI strategy of GNNs and LLMs is that it adapts so easily across massive global industries. In banking, it catches complex card-not-present fraud. In e-commerce, it dismantles those fake review rings. In insurance, it can actively link claimants and providers to catch staged medical claims that share suspiciously similar narratives. It can model rapid account takeovers in telecom SIM swap fraud. And it can parse wallet metadata to explain highly coordinated crypto wash trading. It's incredibly versatile. Ultimately, it all comes down to this core idea. A bare 0.87 risk score doesn't help a fraud analyst. An explanation is what actually gets adopted in production. Providing an undeniable, clear narrative justification is literally the sole reason these advanced AI pipelines ever make it out of academic papers and into real-world enterprise production systems. Which leaves us with this final thought. We already know that fraudsters use adversarial adaptation. So if bad actors start weaponizing LLMs themselves to generate flawless, synthetic camouflage, perfectly mimicking legitimate network behavior and human text, can your detection architecture adapt fast enough to catch them? Honestly, that is the next frontier in this AI arms race. Thanks so much for joining me on this explainer, and keep exploring.